So this talk comes out of a bunch of research that I was doing last year, trying to find a better way to do load balancing. Trying to find a way so that we as a CDN, right, we have to talk to a lot of customers' origin servers. It's like 30,000 of them, right? And so trying to figure out the best way to do load balancing in like an efficient manner, right? Because I realized that like what most people are still using at this point is random or round robin. And that struck me as odd, right? Like, we're a bunch of like really talented engineers, and that's the best we can do, random, like just pick a server at random. It's kind of weird. So I guess spoilers for this talk, I don't really have anything to sell you in this at all. Like, I don't have a solution even. Though there are some ideas as it goes on, but it's mostly just informational. Like, I wanted to understand why I was seeing the weird latency characteristics that I was seeing. And so I started digging and continued digging for months until I had a good idea of what was happening. It may also have to explain some performance problems that you'll see and not really understand. So, right, I'm Tyler. I'm the CTO of Fastly. You can argue with me on the internet right there. Mostly what I do at this point as CTO of Fastly is run interesting projects. Things that may fail is the way that I describe it, which is lots of fun. So, right, what is load balancing? It's a thing that we all take for granted. It's a thing you just you install it on a server, or you you pay somebody to do it, and it's just black box. It just happens, right? So I was gonna do a diagram, but I kind of ran out of time. Right, instead I'm gonna do an allegory. It's the allegory of load balancing. So okay, so almost everybody here has probably been to some sort of sporting event, right? Some sort of stadium, large, maybe it's actually a play or something like that. And there comes this moment, oh right, I wanted to mention, this is actually a story that was told back in 1998 by a guy named Hooman Beheshti, who was formerly the CTO of Radware and Strangeloop, and now works on my team, haha. Right, so everybody's been to a sporting event of some kind, right? And there comes this moment during every sporting event or play or really whatever, where everybody stands up because it is halftime, or it is the break, right? And everybody stands up, and they all want to go out into the hallways and do what? They want to get a beer or something, some sort of beverage, right? So you stand up and you walk out into the hallways, into the corridors of this thing, and you have many choices before you, right? You have this stand here, you have that stand over there, you have this one here. Maybe not all of them have the type of drink you want. Maybe some of them have a line and others don't. Maybe some have longer lines than others. Maybe some of them, though, have more people working behind them than others. So the question is then, would it be more efficient for you to go to this stand right here, or to walk further to go to this one with a shorter line? But then, yeah, so it's you're basically attempting to load balance people and beer in this case, right? So this is actually, this fits what load balancing is fairly well. But why do we load balance? As far as I can tell, there's three major reasons why we even care about this thing at all. And the first two are far more heavily weighted than the others. So there's abstraction, right? We want to be able to treat many servers as one thing. We want one entry point. We want to just be able to pretend that this is all one system. The second would be failure, right? We want to be able to deal with the fact that servers fail all the damn time. And you want to be able to deal with the fact that you have to then remove it and then be able to add it back in. And so load balancing is a way that we do that. And a distant third to this is actually the balancing of load. And that struck me as odd, but it really is a thing that most of us don't actually think about that much or care about that much. As somebody was just telling me right before I walked in here, that he describes it as load distribution instead of load balancing, because it's just not a thing that he cares about, right? Which then leads me to why we end up at random, right? So the good thing about random is that it actually solves those first two cases really beautifully, right? It's simple. There are very few edge cases. You can do failover really, really easily. If you want to add a new server to your random load balancer, you just add it in, and it starts randomly getting traffic, and that's great, right? It also works identically when you have multiple load balancers. If you have two load balancers doing random, it's still random. It's the same thing, right? Super simple. What's bad about random, though, is latency. And this is actually what most of this talk is about, like why random load balancing and why load balancing in general is detrimental to latency a lot of times. So let's talk about why that is. How many people here have heard of the balls into bins problem? Yes, a few of you. That's actually more than most, the other couple times I've given this talk. And so that's exciting, though, because I can introduce you to a really fun probability theorem idea, right? So the statement goes like this. The problem goes like this. If you throw m balls into n bins, what is the maximum load in any one of those bins? So it doesn't specify how we choose the bin, but that's fine. Let's assume random for now. The obvious answer is m, right? But that's incredibly highly unlikely. So really what this question is about is what is the answer with high likelihood? So I'm okay, this problem seems to fit load balancing pretty well. Let me go do some research and see if I can figure out what is the answer to this? How can I figure this out? So there's a paper, Balls into Bins, a simple and tight analysis, that great, I can just look at this and solve my problem. Fantastic. So okay, so let's see. For the case that, let's see, yeah, there you go. Okay, so for the case that m equals n, it's that, great, easy. If m is greater than or equal to n log n, that's the answer. Okay, cool, cool. But more generally, it's that. And I saw this, and I was oh, God, no. I don't even know what a polylog is. I'm not a mathematician. I'm sorry. I'm just a straight-up engineer. So I did the thing that any self-respecting general engineer would do, and I wrote a Python script. Right. So this is just a really simple modeling of this problem. So we have our number of servers n, 8 in this case, and we have our number of requests m, 1,000. Cool. Great. So we make our bins, and then we generate n random numbers and choose the bins for each of them. Easy enough, right? And so you might be expecting that when I print out those bins, they're going to be fairly similar to each other. You know, I mean, it's just a uniform random distribution, right? But it turns out that the variance is actually quite high. Much higher than I expected when I first started doing this. I'm is there something wrong with my code? And I started thinking about it. I'm no, this actually does make sense. It's not choosing them one at a time. It's choosing them randomly, right? It's uniform random, but it's random still, right? So in this case, our lowest bucket ended up with 100, and our highest bucket ended up with 148. It's a really high variance. But this doesn't really model load balancing, right? There's some problems with this. For instance, every request doesn't take the same amount of time, right? Okay, so let's modify this a little bit. Okay, so minor modification here. Now instead of just choosing, instead of just incrementing each bucket, each bin by 1 each time, now we'll increment the random bucket by a random number between 0 and 2, right? So it should be roughly the same because, it's still pulling that from a uniform distribution. Similar results, but actually, in many cases, actually worse. But this still isn't right. This isn't right either. So really, this comes down to the question of how do you model request latency? So yeah, before we can actually answer this, we really need to have a good model for how this works. So another way to state this problem is, what do Erlang and getting kicked by a horse have in common? Anyone know? No? Damn. Poisson processes. So a Poisson process is, well, I'll describe exactly what it is as we go through here, but it's used in a wide variety of different settings, right? Basically any natural process. So this is used to model the probability of trees in a particular area of a forest. It's used to model the likelihood of a new star appearing in a particular section of the sky. It's used to it's used to figure out the rate of arrival at checkout counters at grocery stores. It's a really, really useful and interesting thing. Basically, anytime there are a large number of actors making independent decisions, it ends up following what's called a Poisson process. One of the earliest uses for Poisson processes, oh, right, sorry, backing up. Poisson processes were actually discovered by Erlang, the mathematician, in like the mid-1800s. So one of the first uses for this, though, was by another researcher who was studying the frequency of deaths in the Prussian army by horse kickings. And so that is what Erlang's and horse kicking deaths have in common. So, right. So when we talk about the rate of arrival of requests at a server, we often think about it like this. If that's 1 second, that's 150 ticks on there, so it's like 150 a second, right? But then you might think about it and go, well, actually, it's a little bit more random than that, right? It's not gonna, like, they're not arriving each at like the exact like microsecond, right? So like maybe it looks more like that. But it turns out that it doesn't even look like that. That's a uniform distribution. A Poisson process looks more like that, right? So things tend to bunch. What a Poisson process is, it's a way of measuring the inter-arrival times of requests or packets or whatever. And essentially what it comes down to is that it's exponential, right? So most of them will tend to fall in like a very small, like will tend to have like a very small difference in their inter-arrival times, but then there will be large gaps between them. And so they bunch up. And so what that ends up meaning is that even if your application has perfect constant response times, it doesn't. Because when the request arrives, it's not arriving at like, and then by itself, essentially. The requests are bunching up together, which means that you're not just processing one request at a time, even if you have like the capacity to do that. Which means that some requests are waiting, which means as soon as you introduce Poisson process to this, even if your response times are constant, it's immediately going to start following an exponential curve. That exponential curve might not be that bad, but like immediately that's what happens. And the interesting thing about this is that this just like gets worse and worse as you start building systems, right? Packets follow a Poisson process, which means that like your requests are also following a Poisson process. And so then when your system actually finally gets the request, it's making requests to, say, your database or your like memcache server or whatever else. All of these things follow that same process. And so over time, they build up into like a pretty strong exponential curve. And that is why your latencies always follow that exponential curve. So what is typically used in describing an application's request latency distribution is the log normal distribution. I had read this before, but I wanted to test it. And so this is typically what that ends up looking like when I pulled it out of like various services that our CDN runs. And so this has a mean of 1, 50th percentile of 0.6, 75th of 1.2, 95th of 3.1, and it gets, oop, go back. God damn it. Okay, anyway, so basically it follows this curve like in a pretty nice way, but like up toward the higher end, the 99.9th percentile, it tends to get really bad, right? So when I first gave this talk, someone tweeted at me afterward explaining that what it actually is it's a fat tail, not a log normal distribution, if this matters to you. And I responded saying that, well, you know, this is actually like, this tends to follow the thing, and this was the response I got. And he's totally right. He's totally right. It actually tends to actually follow a fat tail distribution. But I don't care. I'm moving on and using this one. It's close enough. So here are, just to like give further proof to this, these are some examples that I pulled from actual real live sites that are using our CDN. I'm not going to explain who they are or anything like that, but just like general categories. And they all follow this curve. The curve has different like sigmas, in this case, different factors that go into it, but it all follows that same curve. Right, so what we can do is we can go back to our example, and we can tweak that to use a log normal. And so what happens now? Well, it's even worse, right? The variance is even higher than what we thought before. That's basically the same thing, yes. Okay. So this is why perfection is impossible. You can't know ahead of time what length of time each request is going to take. You can't tell ahead of time the load that that request is going to cause in your system for multiple reasons, but like the primary one just being that that's just how systems work across like non-real-time networks. As soon as you introduce a Poisson process to it, this is what happens. So why is that a problem? Well, if requests take an amount of time that is indeterminable from the load balancer, it means that you end up queuing. Or it means that you end up with parallelism and scheduling problems. It means that you're trying to share resources at the same time with each other, right? So just to like really like put a point on this one, let's say we have some computers. Look at those happy computers. They're so optimistic right now. They don't even know about what's about to happen to them. We have here our sad little load balancer, right? And so each of these computers actually has a queue. They have like a request queue coming into them. And so if we knew the size of the requests in the queue, which they look like this, the obvious answer would be that we would want to choose the third one, right? But we can't actually know that ahead of time. And so all we know is the number of requests in the queue, potentially, right? And so the answer is that we choose one becomes sad and falls over. Such a sad computer. So what effect does this actually have? Well, right. The actual, so I started running like more complex simulations of this problem over time. And so like the green line here is the actual distribution. Like I'm like imposing a distribution on the request, on the response times for the requests coming into the system. And that's what it looks like, the green line. But as soon as you run that through a random load balancer, and this is at 70% of the theoretical capacity of the system, you start to see that curve getting higher and getting taller and getting steeper there. Not great. But why does that matter, right? It seems like, 50th, 75th are still pretty reasonable, right? But who here has heard of Gil Tene before? Yes, one. Awesome. Okay. So Gil Tene, you should totally read his blog. It's really, really good. It talks about like how to like model request latencies in like a really intelligent way and how to like measure latency more intelligently. Right. So this is why the 99th percentile matters, right? So the probability of a single resource request avoiding the 99th percentile is, of course, 99%. Easy enough. It means the probability of all n resource requests on a web page avoiding the 99th percentile is 99% to the n. Which means that at 69 requests, you break that 50% barrier, which means more than 50% of your users are going to see the 99th percentile of latency at least once during the page load time, which was super surprising to me. And so like, I knew that like, the number of requests on each page like across the internet was like starting to rise over the past few years. And so I went and looked. And so like, if you go to Amazon, and these are all like before like load on pages, right? So if you go to Amazon, there's over 100 requests before the page load happens. I went to like a particular conference website and there was 190 on there. I went to Facebook, which had over 200 requests before the page load. CNN has 700, which means that they're not just hitting the 99th percentile on every page load, they're hitting the 99.9th percentile. It seems crazy to me, but anyway. So it turns out that like, one of the more interesting parts of this is what happens when you start to increase the load on the system. That curve that I showed earlier was at 70% of the theoretical load of the system. But as the load increases, this actually gets worse and worse and worse. And so, like in this particular example, so over on the left side here, we have like 50% load, and then we have each of the different colors represents a different percentile of like response latency. Okay, so like the 99.9th is the dark blue there, and so like at 50% load, it's not that bad, right? It probably follows roughly what the curve should be. But as you start to increase the load, it gets worse and worse and worse, especially at the higher percentile. So at 90% load, your like 99.9th percentile, if you're doing random load balancing, can be really, really bad. But this is like interesting to me because it means that like If you're not seeing this, it probably means that you're over-provisioned. And if you are seeing this, it means that like if we could find a way to do it better, you could either reduce your latency by a lot, or you could potentially turn off a bunch of servers, both of which would be pretty rad, right? Okay, so what do we do about it? Well, so join shortest queue is another load balancing technique that people use, right? And so this is a graph comparing join shortest queue to random simulation, again at that like 70% load rating. And like it is a lot better. It's still not perfect. It's never gonna be perfect, but it's a lot better. And like it's probably roughly the best that we can do for most circumstances. So there's another way that we can look at this though. So what this graph is showing is the application server load over time for that same simulation. So what this is saying basically is that like each of these lines is the current number of requests that are outstanding at each of the servers, right? And so basically what you can see here is that there's a high amount of variance because of that randomness and because requests build up. Basically, and then the red line is the like mean, and I believe the black line is like the standard deviation there. So basically it's like a very high variance between the servers. With join shortest queue, it looks more like this, which is a lot better. So very low variance. It's still not perfect, but it's probably roughly the best we can do in most circumstances. Another way to look at this is, again, this like the variation as load increases, right? Join shortest queue being on the bottom here, you get like up to the 90% load, and it actually still looks roughly similar to what the like latency distribution should look like. Cool. So let's throw a wrench into this whole problem. Distributed load balancing. Because most people don't actually run one load balancer. No one wants to have a like giant single point of failure in their system, right? You run multiple. Maybe you run many. That's basically my job. I just run a whole bunch of load balancers all day long. So distributed random, as we discussed earlier, is exactly the same. No communication is necessary between the servers. It's just random. You just keep doing random all day long. It's great. That's like one of the really nice benefits of using random. However, distributed join shortest queue is a nightmare. And that comes down entirely to the fact that it's stateful. Like every other kind of distributed system, as soon as you introduce shared state into it, it gets a lot more complicated, right? So basically in this case, if we wanted to do a distributed join shortest queue, we need to be able to share the like each individual load balancer's view of what like the queue's lengths are with each other, right? You have to somehow distribute that information, right? But if you do it in a way that doesn't take into the fact that does not take into, sorry, if you do it in a way that does not take into consideration the fact that as soon as you share that information, it's already outdated, you end up with something like this. So this is, again, that like the load on each one of the individual application servers when you are just sharing like essentially like a naive join shortest queue. Essentially, what this was simulating was I have a bunch of load balancers. They each will periodically tell each other what they believe the current application server loads are. And then they just, each of them just trust that as if it's true, right? And so this ends up looking like that. But like, what's actually going on here? Right, okay, so like we can actually pull this apart and look at it. So this is that same information, but like now each of the lines are separate, right? And so you can see what's happening here is you're getting oscillations. You get oscillations in this case because as they share their information, as you share the information between each of the load balancers, they all have a single view for a brief second there, and they go, oh, that application server is like has the shortest queue. Let's all send our like requests there. Oh shit, that one now has like way too much. Let's send them all over here, right? And so you end up with this wave pattern going on there. Highly unfortunate. So we can do this better though. There's a pretty amazing paper. It's actually like a PhD thesis written by Michael Mitzenmacher called The Power of Two Choices in Randomized Load Balancing. It was actually published like all the way back in 1991. But the claim in here is that it actually like should reduce that variance exponentially. That's pretty cool. Must be a really complicated algorithm, right? No. It turns out that like basically all the paper is, all like the algorithm that he describes is this. Okay, you pick 2 servers at random, and you choose the shortest, like the one that you believe has the shortest queue. That's it. That's the entire algorithm. Okay, cool. Let's see what happens. So this is the code from earlier. Okay, cool. Still looking bad. Great. And so that is the change that we introduce in order to introduce the like power of 2 choices algorithm. That's it. That's all of it. 2 lines. So what does that do? Well, I know you can't really see that there, but I will show you on the next slide. So the top one is the previous example, and the bottom one is the new example using the power of 2 choices algorithm. And you can see that, in fact, it does reduce the standard deviation, reduce the variance between them by a whole hell of a lot. It's super impressive to me. Like, I can't believe that it's actually that simple in a lot of cases. Really neat. So you can see here, this is, again, back to that same example as before, where we have our random line at 70% load. We have our join shortest queue line, which is green. And now we have our randomized, our power of 2 choices, join shortest queue, which actually ends up splitting the difference between them. Neat. But the difference actually becomes more pronounced as the load increases on the system. So here we have the power of 2 choices in the middle. We have join shortest queue in the bottom, and we have random on the top. And you see that even as you approach 90%, 80%, 90% load, it actually is still making a really big difference. Great. That's really cool. So it turns out that people have, despite the fact that this is actually working pretty well, people have continued to try to make new approaches for this. So Mitsumacher published another paper, How Useful is Old Information. There's a similar one, Interpreting Stale Load Information. And both of these actually take a really interesting different approach to it, where instead of just blindly choosing 2 at random, instead what you attempt to do is, in addition to just looking at it currently, looking at the load on each of the servers currently, you try to project based on the current rate of requests where they're going to be, right? So you can say okay, I got this piece of data, I got this this information from this other load balancer 1 second ago, and I know that the number of requests that are coming into the system is this rate, and so I believe that what will have happened by now is that it should look like this, whatever this is, right? And so this actually does, I did simulations for this, I don't have graphs for that, but it does improve it beyond the power of 2 choices algorithm mildly, a little bit anyway. It's cool. There's another one that came out a couple years ago called C3. This was actually an attempt at doing a better load balancing algorithm for Cassandra, which was pretty neat. This one actually attempts to take a bunch of the ideas from multipath TCP and bring them into load balancing. It was so complicated that I could not actually get it working. I tried actually for multiple days to write this into a Python program and failed. So if you can do it, that's great. I would love to know how good it does, but I couldn't do it. I'm sorry. There's some other crazy ideas though as well. This paper came out last year from Microsoft Research called Join Idle Queue. Sargon looks confused. Was it? I really thought it was 2015. God damn it. All right. 2011, thank you, Sargon, but basically flips random on its head. What it does is, instead of having the load balancers choose which server to send it to, you instead have these servers tell a random subset of the load balancers when they are available, when they're free, when they can take another request. And so it turns out that you can actually just, add this information onto the response headers of something, of the responses you're sending back. And so it's actually pretty straightforward to implement. Their argument is that the app servers know their load better than the load balancer does. My argument is that it doesn't matter, and that in fact the load balancer's perspective is the one that does matter, because that's where the requests are going through. Just because a server thinks its load is low doesn't mean it actually is low and that it's responding quickly. But it turns out that their results actually look really impressive for this. So here, the pink line, you can see is random. SQ2 is actually the same thing as the power of two choices algorithm, which kind of splits the difference there. And then their joint idle queues come up even lower than that, which is pretty rad. So maybe that's the future. I don't know. Right, so why does this matter? Mostly it's just that it's interesting. I just found it fascinating to work on and fascinating. And like, I basically just didn't want this stuff to like continue to sit on my laptop and like only have like me know what I like looked up. So hopefully this was useful to you all. Hopefully it's like interesting at the very least, even if not practical for your like day-to-day life. But one of the other interesting things that that I gathered from this is that for many of these algorithms, open source implementations don't exist, which means that we're still using random even though there actually is better stuff out there. So if you're the type of person to go work on some open source like load balancer projects, you should totally implement some of these. It would be great. Anyway, that's all. Thanks. I will happily repeat. Yeah.
What are the best algorithms available in things like HA proxy or yeah, like the current open source?
Yeah. So like, all right. So the question was, what are the best algorithms available in like current open source load balancing projects? As far as I know, like HA proxy doesn't have any of the more intelligent algorithms implemented. I think they were talking about it a while ago, but I don't believe it ever actually happened. Varnish doesn't. Apache, as far as I know, doesn't. Like most of these are still just using random and round robin, and then occasionally you have consistent hashing, which is a whole other thing. So yeah, it's sad. Yeah.
Did you do any experiments with direct server response load balancers and how to get the data necessary to evaluate performance of the server?
So the question was, did I do any research with direct server response load balancers? No, I did not. Sorry. Actually, I would love to chat with you afterward to hear more about that, if you have any like knowledge about that.
Very old.
Sure. Yeah.
Sorry, two questions. One for the joint shortest queue, to what extent does the buffer size have an impact on that, and things like buffer bloat, coddle, stuff like that? And my other question was that I've not looked at this from your scenario of load balancing, but last time when I was looking at this stuff, what I seemed to learn was that Poisson wasn't necessarily always the best distribution for this sort of traffic, and sometimes you need to use something like Vital, but that's much harder to do the analysis on, so I was wondering whether you came across that as well.
Yeah. So right, two questions. That was, I've lost track of the first one already. Jesus. Oh, right. How does joint shortest queue affect like buffer bloat, and like to what effect does like the buffer size come to do with that? And then the second question was about, man, speaking is hard. Oh, right, Poisson versus the Weibull process. Right, sorry. The first one, I don't actually know. I'm not sure that like I didn't really look much into like the actual individual queue sizes. In most of my like simulations, I assumed that the queue sizes were like infinite, right? Because essentially, if you don't do that, then you either have to fail the request or you have to retry to something else, which kind of is weird and skews the results. So I don't have an answer for that one either. The second one, yes, I totally did run into the fact that like Poisson is probably not the best way to do it. The Weibull process, I believe this is actually published back in like 1995, right? And in this case, they were close enough that it doesn't really matter. But yeah, if I were to do it again, I would probably use a Weibull process instead. But yeah, fair question. Anything else? Sargon?
I'm really curious as to, like, when you take the approaches that are in the tail at scale paper, the Jeffing paper, how does that affect all of this?
Man, it's been a long time since I read the Tail at Scale paper. Do you want to like explain that one?
Like the idea that you can have two requests based on another.
Oh, right.
Go dispatch and stuff like that.
Oh, right, okay. So Sargon's asking the question about like the Tail at Scale paper, which talks about like racing two requests against each other. So I did run simulations of that, and that actually is probably better than almost any of this. I just felt that it was probably not applicable for most people. But basically, like if you can run, even if you're doing random, if you can run two requests against each other, like run them simultaneously down to two application servers, you dramatically reduce the amount of time that you spend. It's like incredibly impressive how well that works. Yeah, good point, Sargon.
Do you know of any approaches that look into, I guess, so looking at which request is coming in and giving an estimate of the weight of that request based on where you know it's going?
Yeah, so the question is about like being able to guess how long a request is going to take from the load balancer, basically like looking at something about the request to tell. So I've given this talk a couple times before, and I get this question every time. I probably should just build it into the talk at this point. But so, okay, you can do that to some extent, right? If you can tell, like, you know, which requests are going to take longer than other, maybe you know, like certain admin, like, you know, request paths are going to be like much heavier weight than other ones, right? And so you can do that, but the problem is that even when you segment the requests like that, each of those segments is now going to follow an exponential curve, right? And so you end up with a very similar problem. And so I know that internally, I know that Google was doing this for a while, or at least like playing with doing this for a while, and they ended up ripping it out because of the fact that when you get it wrong in that case, it makes the whole system much worse. So in short, yeah, like it's possible to do this to some extent, but like it ends up not working all that well, for what it's worth. All right, thank you all.